finding extreme values or verifying that values are extreme on or for a three-dimensional surface. One way is just by investigation, but it's kind of a pain, and it's also immediately followed with a series of rules that allow you to kind of bypass that need. So let me talk to you about different relationships. What we can do first when we talk about extrema, and you can read the whole blurb about local extrema, but it's basically, if you think about it in the way you did calculus, or I'm sorry, single variable calculus, it's the high point, the low point, top of the hill, bottom of the valley, that kind of thing. Same idea, but in 3 dimensions. The critical point takes on a little bit of a different meaning here. The critical point the point is critical if both partials are equal to 0, or one or both of the partials do not exist. That would make your point critical, right? So the one that we tend to focus on more, because it's the one that kind of it bears fruit more frequently, is this bad boy. All right. So not only do the first order partials need to be equal to 0, they also need to be equal to each other. All right. Now we know, this is from Calc 1, we know that if there's if you have a local extrema or extremum, then there is a critical point at that location, but it's not always true the other way around. Right? Just because there's a critical point doesn't mean that it necessarily leads to an extreme value. Right? It could lead to something called the saddle point. Right? So if you think in terms of the second derivative in Calc 1, the case where you would have a point of inflection, a saddle point kind of takes on that role in 3 dimensions, right? So if you really kind of expand concave down and concave up into 3 dimensions, that transition from one form of concavity to another is that transition is known as a saddle point, right? The second derivatives test, that's where we kind of make our money in this topic. All right, so this whole shabiggity bangity boom here, and there's a lot going on. I didn't put the drawing tool on. That was dumb. And I could read the whole thing to you, but it's basically saying find critical values if they exist, and then follow these rules. Right, the key component being this discriminant. Right, it allows us to make a determination of whether or not that critical value is going to be a meaningful number in terms of finding extreme values. Right, so I find or have found that the best way to understand this topic is by diving into an example, especially one that doesn't involve us pulling out our hair trying to find the actual derivatives, but just something relatively simple and straightforward. So here we go. So I'm going to figure out f sub x, f sub y, so first order partial with respect to x, first order partial with respect to y. With respect to x, I get negative 2x. The y's go away because they're standalone y terms, which is great news. So negative 2x plus 2. Any constant goes away also. All right. Then negative 2y plus 6. Now, they need to be equal to 0, and they need to be equal to each other. Don't overcomplicate it. You could set them equal to one another, but then you run into the issue of you have an equation with 2 variables. You don't want to do that. What you want to do is you set f sub x equal to 0. You get negative 2x plus 2 equals 0. Now, sometimes your partials will have both x's and y's in it. There's a different approach for that. All right, but we'll handle it this way for now. So 2x equals 2, x equals 1. Then I set my first order partial with respect to y equals 0. Oh, I meant to write, that was dumb. And so blah, 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 y equals 3. All right. So if x is equal to 1, then the first order partial with respect to x would be equal to 0. If y is equal to 3, the first order partial with respect to y would be equal to 0. 0 is equal to 0, so therefore f sub x would be equal to f sub y. All right, so we got what we need there. I also need the second order partials in order to find my discriminant, right? So we have, and you know, the critical point, you know, it's there's a whole blur there. Suppose that f of x has continuous second order partial derivative in some open disk containing blah, blah, blah. Yeah, that's all well and good. What we got here was a critical point. One, 3. That's all you need. All right. So my second order partial with respect to x, very nice and simple. -2. With respect to y, -2. Also need my mixed. Right. So, you know, pick your poison, doesn't matter which one. I'll do f sub xy. So I'm taking the derivative of this one with respect to y. Everything in that expression is treated as constant. So this mamma jamma ends up being a 0. All right. So in terms of, you know, the quality of the question, you know, it's fairly simple. Look at it. Look how cleanly it worked out. I mean, you think about that one with the trig in it, it was a nightmare. You know, and actually, nightmare in terms of, you know, carrying out the process. But, you know, would it have even bore fruit in terms of coming up with critical values? You know, those expressions are pretty nasty. All right. So here, what I want to do is I want to find a discriminant. So d sub 1, 3. And so I'm looking at this one over here. All right. So my second order partials with respect to x and y. So it's telling me to substitute a and b into my second order partials with respect to x and y, respectively. There's nowhere to substitute in. These are constant. So this is just going to be -2 by -2. All right. So at some point down the line, I'll show you where this formula came from because it's Pythagorean in nature, so it's kind of cool. Its origin story. But for now, you know the drill. Not the drill. So f sub x comma y with a and b substituted in, but same deal. F sub x comma y, f sub xy is what I meant to say, is equal to 0. So this is really just 0 squared. So my discriminant is just a 4. Okay. So when I look at my second derivatives test, I'm really just looking at the first two possibilities. These are the only two that would come into play where my discriminant is greater than 0. All right. Then I look at my second order partial with respect to x and determine whether that's positive or negative. So f sub xx it's -2, so it's less than 0. My discriminant is 4, so that's greater than 0. I'm not even going to bother with the a comma b because it was all constant. All right. So looking at this, I would say that it's the Roman numeral 2 there, where we're looking at the discriminant being positive and my second order partial with respect to x being negative. Therefore, there's a local maximum. So therefore, local max at 1, 3. And then what I like to do, just to save myself time, energy, and sanity, f of 1 comma 3. So it's basically me saying I got the a value, the b value, so x comma y, comma whatever z is when x is 1 and y is 3. All right. So I kind of, save myself the energy. Some questions will actually say that, that you can write it in any form. And some of them will say that you need to have it in a simplified form. So you kind of just follow the directions. But in this case, what's the big deal, Otherwise, you'd have to replace, and it's not difficult, but you'd have to do it. Every x with a 1 and every y with a 3. And then simplify and you get your result. It's like something in the negative 20s, I think, if I remember correctly, but it's not necessary. So let's take a look over here. It's something a little spicier. Find and investigate the critical points of a trig function. Now, this is like a 3-dimensional rendering of an egg crate. And so you got multiple highs and lows here. And so we got to kind of play it out here and see if we can make it all make sense. All right. So again, I like to write it as f instead of f sub x, or f of x comma y. So cosine x sine y. So my first order partial with respect to x, and I need my first order partial with respect to y, knowing full well that I'm going to have to come up with second order partials anyway. All right, so hanging on to my sine of y, the derivative of cosine x is negative sine of x, so negative sine of x. All right, so again, that was hanging on to the sine of y because that one was treated as constant, and then differentiating that one here, differentiating the x component. So now we're going to hang on to the x component, cosine of x, and differentiate the sine of y, which is cosine of y. Okay. So we're looking at something obviously, I don't think you need me to say this, but I'll say it anyway. We're looking at something obviously a little bit more complicated. And that's part of the fun. Right. Oh, my highlighter. Where we go? One. So cosine x got hung on to. And since we need our second order partials, we might as well just grab them before we get too far ahead of ourselves. So I need f sub xx. So again, hang on to the x component. So I'm sorry, hang on to the y component, negative sine y. Cosine x, f sub y. So hang on to the cosine of x component. Derivative of cosine of y is negative sine of y. And then we need the mix. So I'll just kind of chuck that up above. F sub x, y, yx doesn't make a difference. For that one, I'm hanging on, I'm looking at this guy here, hanging on to the y, I'm sorry, the x, the sine of x, differentiating the y, sine of y is cosine y. I also have a negative sign, comes along for the ride. I got all my second order partials, so that's all good. All right. So I need my critical values. And I get that by taking my first order partials and setting them equal to 0. So negative sine y, sine x, set equal to 0. I'm going to do the same thing for first order partial with respect to y, cosine x, cosine y. So when I set these equal to 0, it's like they're quadratic, basically, you know, two first degree factors. So I set each one of those factors equal to 0 and solve. I get sine of y. Just write it, yeah, sine of y equals 0, and sine of x equals 0. And cosine of x equals 0. Cosine of y equals 0. Now, what I'm going to do here is something a little bit more logic-based. And that is introduce logical connectives, because in order for this to play out the right way, we need f sub x and f sub y to both be equal to 0 under the same condition. Right? Or consistent with one another. So I'm going to throw in an and symbol here. So I need this relationship to be true and this relationship. So this, you know what? I got to figure out a way to change the default on this. Like, I very rarely want any other figure aside from the regular ones. That I can just move that here. It's just NYU wanting more money. I haven't finished paying them for the first go round, so why am I going to give them more money? So those two have to be true concurrently, which means that these two have to be true, these two sets and these two sets. All right, but within each set, in order for those quadratic expressions that are set equal to 0 to be true, either part needs to be true. So or quality or, but I'm going to live with it. Or. All right, that's going to be important in a sec. So I'm just going to kind of hold that thought. So for now, what I'm going to say is, all right, we're thinking in terms of the unit circle. And, you know, just for the sake of having something to point to, I'm going to draw a quick circle. And I'm going to end up moving it off on the side in a minute, but we have 0, we have pi over 2, we have pi, 3 pi over 2, and 2 pi. Coordinates here, 1, 0, negative 1, 0, 0, 1, 0, negative 1. Just again, so I can point to something, right? So when I'm talking about sine of y being equal to 0, I'm talking about the sine value. Sine is the y, you know, coincidentally, it's the y in the ordered pairs working their way around the unit circle. So any instance in which the y value is equal to 0 is going to be true. Right? So I'm looking at y would be equal to really just anything along the x-axis. 0, pi, 2 pi, and so on. And the same would be true for x because it's still a sine function. Right? So x would be equal to 0, pi, 2 pi, and so on. Now for the other quadratic, we have cosine x, cosine y, right? So that's where the cosine functions are equal to 0. So we're talking x. I'll put it in the same order. You know what I'll do is I'll put the x first here. It really doesn't matter. I'll just do a little bit like this. I have x first in both cases. Organizationally, it kind of makes more sense that way. So you have x equal pi over 2, 3 pi over 2, 5 pi over 2, anything on the y-axis, and so on. And the same would be true for the y's. So we have, and all the negative counterparts, right? So it could go the other direction also, right? So this is all plus or minus. So what I'll do is I'll just kind of move this over. Put a little squiggly and say plus or minus. All right, so these are all of our possibilities, and there's a lot, infinitely many, that satisfy this relationship. All right. Now, remember, it's the ors followed by the and. So sine of y has to be equal to 0, or sine of x has to be equal to 0. And cosine of x has to be equal to 0, or cosine of y has to be equal to 0. Right? So there's a lot of mental gymnastics going on here. But if you keep sight of what it is that we're trying to do, so let me just grab this and bring it over so I can point to it. I'll just put it down on the bottom here temporarily. I'll move it later. I'm not getting rid of the problem that follows, but just so I have it. We need second order partials at A, B, A comma B, right? So it's like, okay, where's my A, where's my B? Well, we still kind of need to figure out which ones are going to satisfy this equation. So what we need is something that's going to give us some pairing of values that we can eventually use to generalize, but for now, some pairing of values that'll give us all the different possible outcomes that we can get, right? So looking at this, I would say, all right, well, I need an x value and a y value, right? I need an x value that's going to satisfy the left-hand side, and I need a y value that satisfies the right-hand side, or vice versa. So it's a good place to start. So what I can say is, let me grab, for example, and I'll use a highlighter, let me grab the simplest value that I can, x equals 0. So let's say, and I'll try to distinguish the different cases. So I'll just say case number 1. So I'm going to say x equals 0. So if x is equal to 0, we would have to ask ourselves, okay, what's happening here? Well, it's going to satisfy this part, right? It's going to make my f sub x equal to 0, but it's definitely not going to satisfy the other part, all right? Because there's no way that x can be equal to 0 and cause that entire quadratic there to be equal to 0. So I need a y value that's going to cause it to be equal to 0. So I'm going to pull a y from that set. All right, so an x from my left set and a y from my right set. So let's say I choose y equals pi over 2. I'm looking for the simplest possible scenario in each situation. All right, so what I would want is I got to go down the list here. All right, and so with that, I'm going to move this kind of out of the way. I'm done with that. All this stuff I think is fine, but I can make it a little bit smaller, I guess. I have some room here. You down, you here. All right, so I need f I'll just do shorthand notation f x x, f y y, f x y. All right. So if I pop in a 0 and an x and a pi over 2, I'll use my highlighter for x and y. So if I'm doing f of 0 comma pi over 2, I'm going to get cosine of 0, which is 1, sine of 0, which is 1. All right. Now, since this is an egg crate kind of thing, meaning that it's going to oscillate up and down, like the waves in an ocean. So there's going to be high points, low points, and there's going to be baseline. All right. So this appears to be a high point. So it looks like I'm going to get an extreme value out of this. It's kind of hard to tell. Maybe it could be as high as 2 units up, but it could also be a matter of perspective. So like one of these points here looks like it could be consistent with 1 unit. It's hard to tell, but unless we get something higher, right, that's a reasonable assumption. All right, so I got a 1 here. Now I need f sub xx, right? And all I'm doing is just following along with this, right? F sub xx. So my xx is over here. I'm replacing the sine of y. That's gonna give me sine of pi over 2, right? So that's a -1, but then it's negated again, right? So I'm just gonna, as I get a value in my head, I'm just gonna jot it down so I don't forget it. So I have a negative sine of, what did I say, pi over 2? Sine of pi over 2 is actually +1. I said -1, I meant +1. Cosine of x, cosine of 0 is 1. So this gives me a result of -1. Then I can get into my yy. So that's this guy. So cosine of 0. So I got a negative for the coefficient there. Cosine of 0 is a 1. Sine of pi over 2, a 1. Result -1. And then finally, the mixed, right? So negative built in, sine of 0. So -0 times 0, result 0. And it's kind of the first break in this whole process that we've gotten so far. Right? So as easy as the last one was, this one just, it ramped up the intensity significantly. All right? But that was the hard work for this one situation. So I need my D. D is the product of the ordinary partials. The -1 times -1. And you can see, again, the formula, it's really just the product of the two, subtract from it the mixed one squared. So it's basically the product of each type of second order partial derivative. So you're doing x against xx against yy, then you're doing really xy against yx, but since they're the same, we just write it as power of 2. Right? So that might make it a little easier, right? Or at least to conceptualize. So 0 squared, result is going to be equal to 1, which tells me that D is positive. All right. So our conditions boil down to the D being either positive, negative, or 0, just like a discriminant in quadratics. And our second order partial with respect to x, we want to know what the sign is of that. We already have that information. F sub xx is less than 0. So that tells me, so we're looking at our scenario here, that tells me that we have a local max at 0 comma pi over 2. But the issue that we're going to run into, and it's a very significant issue, is that those are not the only locations in which we're going to have relative max. We have infinitely many relative extrema, max mins, so we have to account for all of them, but we don't want to do this work infinitely many times. That wouldn't make any sense. So we want to generalize. So now that we know that this particular scenario, so something from this group of X values, the ones I highlighted, 0, pi, 2 pi, and so on, and something from the group of Y's in my second category, that led to a local max. So we might have it in that we could say that you have any value, so local max, or just for the max anyway. Any value that follows this relationship, so anything that's plus or minus 0, pi, 2 pi, so that's pi k, right? So that would be my x value, right? So pi k, where k belongs in a set of integers. So that gives you 0k, 1k, 2k, 3k, 4k, whatever. And then any multiple, any odd multiple of pi over 2. So we could do that a couple of ways. The way that we had been doing it was to say, let's establish an odd number, right? So that would be 2k plus 1. And then we multiply that by pi over 2. So put this over a 2, slap a pi at the end, where k belongs to the set of integers. There's other ways to say that. Another popular way of writing it would be pi over 2 plus pi k. You know, you're going a pi movement from pi over 2 based off of the integer position. You can use n's if you want to, and people like to do that too. But either way, so we have a relationship because it seems like anything coming from that first set, the x set for the first group and the y set for the second group gets the job done. So now let's see what we can do for a second possible scenario. So we'll call it case 2. And all this stuff is going to bear out the same way in terms of the structure of it. But maybe now I'd say, okay, well, maybe I grab something from X in my second category and Y in my first category. So just basically flip the order. So X is equal to pi over 2, and this is my test subject, basically. If I pop it into my original function, cosine of pi over 2 is equal to 0. Sine of 0 is equal to 0. That's going to give me a result of 0. All right. Now, if we're assuming that there's symmetry, when we're talking about trig functions, you know, you have your maximum value. Typically, the minimum value is the reflection of that. So if we know that the maximum is at a z value of 1, then a good suspicion would be that the minimum would be at -1. So my guess is that this is going to be that transition point between concave down and concave up. So that makes it seem like a saddle point seems to be in order here. But we'll see. You know, so let's say f equals 0. My first order or second order partial with respect to x. So now we're going back to my x partials. So we're doing this. How am I highlighting this? I'm doing this in green now. I already used green for other things. So I'm popping in a pi over 2, 0 for x and y, respectively. So if I replace the cosine with a pi over 2 in this expression, Cosine pi over 2 is going to 0, so everything else is going to 0. All right, f sub y. Popping in a pi over 2 for cosine, that's going to 0, so everything else is going to 0. All right. And then the mixed bag. Pop in a pi over 2 for x, I get a 1. Negated is -1. Cosine of the y value of 0, cosine of 0 is equal to 1. So we get a result of -1. All right. So now we're kind of at the point where we can tackle our discriminant, and it's going to be a whole lot easier to do that because we've got a lot of zeros. All right. So D is going to be the product of these two guys. So 0 times 0 minus -1 times -1, so -1 squared, which is going to be equal to a 1. All right, so unless I screwed something up. Oh, sorry, -1. I did screw something up because I already know what the answer is supposed to be. It's not the z value is not a -1, so it has to be a saddle point. So I was wondering why on earth that just happened. So, all right. So looking at our possibilities here, if D is less than 0, then you're looking at a saddle point. All right. So saddle point at I already forgot the values, pi over 2 comma 0, comma f of pi over 2 comma 0. Well, actually, we already know what f of pi over 2 comma 0 is. It's 0. And that reminds me, over here, I probably could have written in the 1. All right. So I got my saddle point, then I just got to generalize it. So that's going to be easy. Because I have the saddle point, SP, acceptable abbreviation for saddle point. It's the reverse of what we just came up with here. So a little copy paste action. Just we're going to swap these two. All right, so we have a justification for local max and saddle points. Now we need some sort of way of coming up with local min. All right, so time-wise, debating mental gymnastics here. I'll throw that up there. I'll write case 3. Just wondering, because we're down to the end here and I don't want to keep you late. So you know what I'll do? Yeah, I decided already. Case 3 is the one where we're looking for the local minimum. So what we can do is we'll table that for next time. I'll put a star on this one. So try this on your own. And see what you come up with. Is there a reasonable expectation that you can? Yep, that's what I'm going to do. All right, because otherwise it kind of I run the risk of rushing the explanation because it gets a little interesting. All right, so, all right, yeah, so that's what we're gonna do. All right, because also I really have to go to the bathroom. Oh, cool, that all ended up in the video.